All right, here we go. Find all solutions of the equation z minus 2I cubed equals I. Couple different ways you could do this. You could start by finding the three cube roots of I and then working backwards, or you could expand the left side and try to go from there. I think it's probably better to find the cube roots of I and work backwards. And then I'll go and see if I can expand and figure that out. That might kind of suck. Okay, so let's use a different letter. Let's say that we know that W cubed is equal to I. Then we also know that W cubed is equal to e to the I times pi over 2. And so that means we know that W is going to equal e to the I times, the first one is pi over 6, because that's not Wi. I meant W1. The first value of W would have an angle of pi over 6 because that angle times 3 becomes pi over 2. The second W would be e to the I. If I add 2 pi to the if I add 2 pi to pi over 2, then I get 5 pi over 6. And if I add 2 pi to pi over 2, again, I get 9 pi over 2. And so dividing that by 3 gives me 9 pi over 6. So I kind of skipped a step verbally on that. What I'm doing each time is you're taking your original angle of pi over 2 and you are adding 2 pi k to it, because that will get you to the same location over and over and over again. Adding 2 pi is a full circle. And so my three angles that I used were pi over 2, 5 pi over 2, which is equivalent, and 9 pi over 2. Those are the three possibilities that W cubed could equal. And so if you divide each of those angles by 3, you get my W1, W2, and W3. And so what I know now is that my original problem, z minus 2I, has to equal W1, W2, and W3. So W1, if I write it in Cartesian coordinates, let's see, pi over 6 is like a 30-degree angle, so that becomes root 3 over 2 plus 1 half I. W2 becomes 5 pi over 6 would be negative root 3 over 2 plus 1 half I. And 9 pi over 6 is 3 pi over 2 is just negative I. And that makes sense, right? Because I squared is negative 1 times another negative I. Great. So we have those. And so then what I just need to do now is set up z minus 2I equals the first value. So root 3 over 2 plus 1 half I. So that means that 1, I'll call this z1. So z1 is going to be root 3 over 2 plus 2I would mean I get 5 halves I, or 2.5. Z2 minus 2I is going to equal negative root 3 over 2 plus 1 half I. So Z2 is going to equal negative root 3 over 2 plus 5 halves I. Z3 minus 2I is negative I. So Z3 is equal to positive I. And those are my three roots right there. And it would be a good idea to take those values and actually cube them, or I'll subtract 2I from it first and then cube it to make sure that it comes back as I. But I feel pretty confident about those answers. Always possible that I made a mistake. So that's one approach to doing it. I wanted to see, and you can obviously stop watching at any time, but I wanted to see if I could go the other direction or if it just gets too nasty. And the other direction I mean is taking z minus 2I to the third power and just expanding it out. I think this is going to get kind of ugly. So that would become z cubed plus 3z squared times negative 2i plus 3z times negative 2i squared plus 1. I think this is going to suck. Okay, z cubed minus 6z squared minus 12z. 6z squared has an I on it. This other one becomes minus 12z because 2 squared is 4, but I squared is negative 1, and plus 1. And I'm trying to see if this is equal to I. Yeah, I don't know. Let's see. We could try at this point to write it in terms of r e to the I theta, and then we would get r cubed e to the 3i theta minus 6r squared. Yeah, see, I think this is where it kind of breaks down, is that I can't see, there might be, but I'm not seeing a nice way to then like factor this or solve this. I think that the only approach actually is the other way that I did it, where you find the cube roots of I first and then go from there. Um, yeah, I mean, maybe you could write z in the initial problem as a plus bi minus 2i to the third and try to expand this out, which is like a plus I times b minus 2 to the third. You could try this approach, a cubed plus 3a squared b minus 2i plus 3a b minus 2 squared I squared plus I cubed b minus 2 to the third. You might be able to get through this. I'm sure at this point most people have stopped watching. The real parts would be a cubed minus 3a b minus 2 squared, and the imaginary parts are 3a squared b minus 2i minus b minus 2 cubed I. And actually, maybe we can get somewhere with this because the real parts need to equal 0 and the imaginary part needs to equal 1. So if we set this equal to 0, we can factor out a and get a times a squared minus 3 times b minus 2 squared equals 0. So those are two cases, either a equals 0 or a squared equals 3 times b minus 2 squared, which would mean if you take the square root that a equals square root of 3 times b minus 2. And then the imaginary part needs to equal 1. So if a equals 0, then on the imaginary part, we get that b has to equal 2. Or not quite, no. Let me back that up. Let's actually write it out. Don't try to skip steps. Okay. So if a equals 0, then the imaginary part we have is negative b over 2 to the third equals 1. In other words, b minus 2 equals negative 1. In other words, b equals 1. So that works. That gives us the value of z equals I. And that works, actually. Okay, that's great. If we try the other value there, then we end up with 3 times a squared. So 3 times b minus 2 squared times another b minus 2 minus b minus 2 cubed. That all has to equal 1. That's a lot of, let's see, that's 6 times b minus 2 cubed equals 1. So b minus 2 equals the cube root of 1/6. And then you can backtrack that to get a, and I think it's the same as the other ones, but I think there must be some mistake over here. So, okay, what's the point? It is, I guess, possible to just really work it out with a system of equations and Cartesian coordinates, but I think you will agree that it was much easier to find the cube roots of I and then use polar form from there. So, thanks for watching. Let me know if you see something that I did wrong, and I'll try to clear it up.